Welcome to our webinar entitled Using UniChEM to Find Compounds in Databases. My name is John Chambers and I'm joined by my colleague Anne Hersey. We're in the Kemble group at the EBI, that's the European Bioinformatics Institute, which is part of the European Molecular Biology Laboratory, and we're based here in Cambridge, UK. And here's the plan for today's WebEx. I'm going to go through the first two major items on this list, the basic introduction to UniChEM and running through some of its current content. And then Anne's going to take over and show you some analysis she's done using an extension of UniChEM called Connectivity Search. And then she'll finish off and then we'll do Q&A together. The first two sections, the basic introduction and current content, I've largely dealt with before in other webinars, and we have in fact put a YouTube video of this in far more detail already on YouTube. So if you want to know a lot more detail about the basics of UniChEM, then please go there. It was posted about 2 years ago, but it's not out of date because it just discusses things like the data model we use, the schema, etc. The current content obviously has changed a bit more, so I'll spend a lot more time on that. So this screen just shows you the YouTube video which we currently have out there from about 2 years ago, if you want some more details on the background. So I'm going to run through some of that background, but really quite quickly, just to bring everybody up to speed. So for chemistry-aware databases, usually have a series of compound landing pages, one page for each compound in their resource. This is the Kemble compound report card or landing page for Kemble 12, which happens to be diazepam. And if you just scroll down to the bottom of this page, you'll find a series of links, which are cross-references to the same molecule, but in other resources. And these are automatically generated and maintained by UniChEM Web Services. And that, in a nutshell, is what UniChEM is for, is for creating and maintaining these links. When somebody opens this Kemble 12 report card, a REST web query is sent off to UniChEM, and the information you now see before you is sent back to the browser so that the person sees the most up-to-date links for the compound that they're looking at. Of course, it's not just Kemble that makes use of UniChEM, but other resources use the same functionality. So I said previously that UniChEM is really meant to be used as a web service tool, but there is a GUI Frontend, and if you go to the main page, the home page for UniChEM, it looks like this, and you can put in the same sort of compound, just a moment, you can put in the same query that we did before. In the example I showed you a few slides back, you can put in Kemble 12, you can say it's from the Kemble resource, and you'll get back the data in the GUI very similar to the data I showed you 2 or 3 slides back. This GUI interface gives you a little bit more information, so it doesn't just give you which compounds IDs are equivalent in other resources. It also tells you some of the obsolete assignments as well. So if you look, for example, at the third record down, the drug bank ID DB07699 is no longer currently assigned to the same structure as Kemble 12, but was in 2011. So UniChEM is an archive of identifiers and structures as well as giving up-to-date links. So all these links are created by a complete and full match of the standard INCHI key, and that's the sort of normalizing mechanism that UniChEM uses for creating these links. I said that the preferred method is to use the web services. If you go to the web services tab in UniChEM, you'll get plenty of documentation on actually how to construct these RESTful web queries. I don't really want to go into the details of that, but here's an example of one giving exactly the same data as I did in the previous two or three slides. Okay, so now briefly, why did we create UniChEM? What's it for? About 6 or 7 years ago, we realized that at the EBI we had many resources, all of which had small molecule information in them, but with very different user bases, and they were all being developed at different rates and in different ways. But we wanted chemists coming to the EBI to be able to find information in any of these resources. And so we thought of many solutions. One was to have a central registration system or put all of these resources into one giant database, none of which were really very practical, and we found that the most lightweight solution would be to just to link them independently, let them remain independent, but to create links between them. But creating links between them, of course, is a lot of work, and each of the individual resources have to create links to each of the other ones. So there's a potentially a lot of duplication of effort. So that's why we developed UniChEM, to abstract out all that work and reduce that maintenance overhead. So now people in the EBI, the different resources, submit their identifiers and their structures into UniChEM, and in return get all the links back to the other resources. We very rapidly realized, of course, we could pull in the data from external resources as well. So we did that and enjoyed being able to automatically create links to them. And then it was another short step there to make UniChEM available externally so that anybody in the world can use UniChEM's cross-linking activities. The process for creating new releases is completely automated. In fact, the whole process for UniChEM is completely automated now and works on a weekly release cycle. Doesn't mean to say that all the resources, all the sources coming into UniChEM are updated weekly. Of course not. Some of them we don't have the data, we can't access the data anymore because of license changes and so on. And in other cases, the resources themselves simply aren't updated on a weekly basis. Chemical, for example, is updated on a 3-monthly basis. But whatever can be updated is updated on a weekly basis. If you go to the GUI again and look in the analysis section and go to the top level stats page, you'll get some information on the release number and when it was released, and you'll also see some other top level information such as the total number of structures, currently 140 million, total number of assignments, that's the sort of pairings between a structure and an identifier, and so on, the number of sources. And if you go to the Sources tab, you'll see all those 30 sources, and you can drill down on the hyperlinks in there for a bit more information on those sources and what they contribute. Lastly, the thing I want to talk about is the download section. So you can obtain the whole of UniChEM, download it for yourself if you wish. If you go to the FTP site, which this download link gives you the link to, you'll see on the top panel here that it looks like this. There are 2 major directories, a KNIME directory and a data directory. The KNIME directory simply contains KNIME protocols for querying UniChEM. I won't go into that today. The other one, the data section, if you were to go into that directory and look in there, you'll see 2 subdirectories, one called Oracle Dumps and one called Whole Source Mapping. The Oracle Dumps one I'll deal with now and come back to the Whole Source Mapping one. The Oracle Dumps one is badly named, really, because it does contain Oracle Dumps, but it contains other things as well. So I'll just to make you aware of that, and I'll show you what it does contain. But in this directory, there's a listing of all the recent releases of UniChEM. We keep the last 5 releases and all releases numbers divisible by 10. We keep them as an archive. But if I drill down into the most recent one, the UDRI 134, by the way, UDRI is synonymous with release number. So if we go to look at release 134, this is what it contains. The second from bottom, the unichem.dump file, is the Oracle dump file. But above that, you'll see a series of text files. These are text file dumps of specific tables within UniChEM. So if you don't have Oracle, you can still import UniChEM data into whatever flavor database you want, but you will have to import them from these text files. There's an MD5 checksum thing at the bottom. If you're not sure how to use that, look at the README. There's READMEs on every level which can explain what to do. The other major directory in the data directory is a whole source mapping directory. And without going into too much detail, basically it contains files which link between the different identifiers of two different resources. So this file, for example, source 3, source 15, gives you all the linkages between source 3, which is PDBE, and Shaw-Campbell. And there's all the possible permutations are computed and dumped into that folder. You just have to find the one that's appropriate for you. And they're updated as and when the data is updated on a weekly cycle as the releases are updated. Okay, so that's my very quick overview. As I say, if you want deeper information on UniChEM, data model, etc., please go to the YouTube video from 2 years ago. But at this point, I'd like to hand you over to my colleague, Anne Hersey, who's going to give you some interesting analyses on connectivity search.
Okay, so hi everybody. I'm going to sort of go through some examples, a bit more about how we're actually doing the mapping in UniChEM, and then just some sort of examples of the sorts of things that I think you can do with the data in the database. So I guess the question perhaps that you might ask is, how are we mapping all these compounds together? Well, basically this is done quite simply using the INCHE keys. So for all the data sets in UniChEM, we're storing the database identifier, the INCHE, and the INCHE key, and we're using the INCHE key to effectively map all these identifiers and hence databases together. So as John showed, you can input either an INCHE key or a source identifier, and then you can get back the list of all the databases and links to those compounds in those databases where that particular compound exists. So just to sort of give you a very simple example, the sort of use case, I guess, is, you've got a compound you're interested in for whatever reason, and you want to know, who's looked at that compound, what else is known about it. So, for example, so long as you can get, either, well, get an INCHE key is probably the best thing, but, if you know that it exists in one of the databases indexed in UniChEM, you can also use that source compound ID, input that into the UniChEM interface, and it'll bring you back a table of data like this. And you can then click on these. These are all hyperlinks, so you can click on these, and then you can actually see the page relating to this compound, for example, on those individual database pages. So we're not integrating the data itself that's in these different databases. It's just more providing links to where there is information in those databases on that specific compound. So I've just highlighted in red a few of the examples here. And so if you clicked on these links, you would basically go to these pages in these different databases. So, for example, you can go to the EPA web CompTox web page, where they've got a lot of information about the sort of toxicity of compounds. You can go to the PubChem page on the compounds. You can go to Chembl. You can go to Shaw-Campbell, which is our patent database, and you can go to pages like eMolecules or Zinc, which indicate how you can actually buy these compounds if you want to actually do some experiments, for example, on that particular molecule. So these are obviously just a subset of the 30-odd different databases that we've indexed in in UniChEM. But, you know, just to sort of give you an idea that it does provide you with these direct links back to the compound page on those different resources. Okay, so that example was just, you know, if you've got a single compound and you want to find information on it. But as John indicated, the sort of one of the big powers of UniChEM is to be able to use web services to do this on sort of large numbers of molecules. So this is just an example of something that I did where I took the set of marketed drugs that we have in Kemble. So this is, you know, just a sort of a subset of them shown down on the left-hand side here, and then just ran the UniChEM web service that then did an exact match lookup across all these different databases that we have in UniChEM, so that you can actually see now coloured in green all the different databases where which have the same compound structure as we have for one of these marketed drugs. And I mean, obviously you can do this for sort of any set of molecules that that you're particularly interested in. So this has obviously applications in terms of, you know, I can look and see whether the compound structure I have in Kemble is the same as for a particular compound as people have in other databases. And I guess if not, I can look at my structure and think, oh gosh, have I got this wrong or whatever. And you know, obviously anybody else can do this. And then I think, as John mentioned, in Kemble we're using the UniChEM web services to provide links. We're doing the same in Kemble, which is our patent database. And I guess this is something that anybody else can do as well. Is, you know, if you've got a database showing something, you can provide links out to other databases using the UniChEM web services. So this is just an example of where we've done this in our Kemble patent database. So I guess that works well, and that's where sort of UniChEM started. But then it became apparent that you could do more than just do these exact match lookups using UniChEM. And just to sort of highlight the reason why we thought this is important is you can take a compound. So this is paroxetine, which is a drug molecule that we have in our Kemble database. But it actually turns out that in Kemble we've got a whole load of other molecules that are very, very similar to paroxetine in sort of fairly subtle ways. So, for example, we have molecules that have just got different stereochemistry. They've got no stereochemistry. We've got different isotopes. So we've got a couple of different tritiated forms. And in Kemble, for example, all these different molecules will have bioactivity data on them. Now, it could be that somebody's genuinely tried to look at the different enantiomers, for example, and different isotopes and measured data on those. It could be that, you know, a mistake's been made, but for whatever reason, it's potentially useful to be able to, you know, have the ability to try and find these related molecules to the molecule that you're perhaps interested in. So it actually turns out that the inches are actually quite inches and inchy keys are actually quite useful for this. So, for example, this is just the inchy and inchy key for paroxetine, the molecule I showed you on the previous slide. And if you take a couple of the other molecules that I showed, one where you've got different stereochemistry and one which shows no stereochemistry, and then you actually look at the differences in the inchy keys for these molecules, hopefully you can see that the first part of the INCHE key is identical in all these cases, and the second part is different. So what this means is that we can use this first part of the INCHE key to link together these molecules on the sort of connectivity level. And I don't know, for people who are maybe not that familiar with INCHE keys, if a compound's not got any stereochemistry, it always has this second part of the INCHE key is always the same. And then sort of potentially what you might think is a more complex example is you've got a molecule here which is not only got different stereochemistry from the paroxetine molecule, but it's also it's a different isotope. And again, you can see that the first part of the INCHE key is identical and the second part is different. So this immediately gives us a way of linking together all of those different molecules. So okay, so that's fine, but I guess one of the other things that we always see in databases is people have tested different salts, for example. So again, these are just 6 examples of salts that we have in Chemble, some of which, the ones which are highlighted in green, are actually different salts of paroxetine itself, and these two, the ones in a sort of bluey colour, are salts of paroxetine, well, are salts of compounds like paroxetine but with different stereochemistry. So potentially, again, it's useful to be able to pull together information that's been measured on different salts, but also these different related molecules and the salts of them. So the question is, can we actually do this using the INCHEs and INCHE keys? And it turns out that yes, we can, by actually looking at the way the INCHE itself is constructed. So if we take, for example, this is a malleate salt, I think, of paroxetine, and you can see from here that not only is the second part of the INCHE key different, but the first part is totally different. So on the face of it, you can't just identify the parents, shall I say, with the INCHE key. But if you go back to the INCHE itself, because the INCHE is built up in layers and also sort of for mixtures, you know, the parts of the two components of the mixture are separated in the various ways in the INCHE key. In the INCHE, you can actually split this out and generate the INCHE of the individual components. So here I've indicated in red the part of the INCHE that corresponds to the paroxetine molecule, and then in black the parts that correspond to the malleate. So if we do this literally with a bit of sort of scripting, then you can actually split this up into an INCHE for paroxetine and an INCHE for the malleate, and then from that you can generate the INCHE keys. And then, of course, if we look at the INCHE key for now our parent molecule, we can see that actually matches the it matches the INCHE key for paroxetine, because effectively this is paroxetine. So by doing this on all the mixtures that we have in UniChEM, we developed what was called a connectivity searching ability, and this enables you to map together things like isotopes, compounds with different stereo differences, compounds that are different charges, any combinations thereof, and then also to be able to do this on all the different components that there are in a particular compound. So, you know, I think there are probably a number of applications of this sort of thing, and, you know, hopefully you'll be able to sort of identify your own example. But, you know, to me, the sorts of things we've been using it for is identifying potential issues when you're trying to check structures and curate them, because, you know, we all know that a lot of these molecules do have very complex stereochemistry, and you know, with the best will in the world, I guess we don't always get all of them right all of the time. So there will be examples where, you know, even for sort of standard drug molecules, different databases have the molecules maybe incorrect, or just actually represent the structure in a different way, because there are certain things that we can't easily represent in the V2000 mol files that we all know and love. So, you know, obviously we can extend what I was talking about earlier, where if you've got a molecule you're interested in, you can search databases and find not only the exact matches, but you can find these related compounds. And then, you know, you can find experimental data on a compound regardless of the salt that's been tested. And, you know, this is an example I like. So Viagra is actually, as in the drug molecule that's sold, is actually sildenafil citrate. So if you put that into a lot of databases like Chembl, you'll find a little bit of data, but not most of it. Most of the experimental data is actually measured on the parent molecule. So having this ability to identify salts of a particular compound, I think is quite useful. So if we took our paroxetine molecule and just put that INCHE into the UniChEM interface, and then ask it to give us back all the connectivity matches, either on the molecule or on any components of salts or mixtures, then basically we get a large number of matches, over 1,000. And you can see from this table here that you get a bit of information that tells you about whether it's the protonation that's different, whether it's the double bond, cis-trans information, whether it's stereochemistry differences, or whether it's the isotopes that are different. So just to pick up on a few examples, these ones where we've got zeros here are where we have exact matches in these databases for the compound that I put in, which was the compound we had in Chembl. You can also pick up examples where you've got the salt exists in different databases. So this is just the GUI page for paroxetine maleate. There are examples where databases have different isotopes. So here's the Guide to Pharmacology example where they've got tritiated paroxetine. And one of the things you quite often find in zinc, because of their interest in docking, is that a lot of the molecules are actually protonated. So in the, you know, for a basic nitrogen, for example, in the form that they're probably binding in an active site. So again, you know, you can identify these molecules using this connectivity matching in UniChEM. So in the same way as we did for the exact matching, you can use the UniChEM connectivity web services to put in, or you can construct queries that enable you to put in lists of molecules and then pull back all the connectivity matches on those molecules in the different databases. So this is just what I did before, just taking a big list of marketed drugs that we have in Chembl and looking at where you get matches across different databases. So just to sort of pull an example out of this, you can see a comparison here for this list of molecules in Chembl, and whether we have an exact match to a structure in drug bank or a connectivity match. And hopefully what you can see is that, you know, by doing the connectivity matching, you're getting a lot more matches than you would have done if you'd just done the exact match. So probably, you know, both these two databases have these molecules in them, as you would expect, you know, because they're marketed drugs, but in some way we've represented these structures slightly differently. And you can obviously do this across any pair of databases, and that's where the whole source mapping that John was talking about potentially could be quite useful sets for people to download if you don't want to run the web services yourself. And then just to show you an extension of what we've done in Chembl itself. So John showed at the start where we've used the web services to do exact links to compounds in other databases, but there's also an option on the Chembl web page to actually look at the connectivity mapping across databases. So if you do that, you don't see the colours here, but I've just tried to do that to sort of indicate the, you know, the different types of matchings that we've got. So for example, this is again paroxetine. So paroxetine itself, which is this molecule here, then matches to these molecules that have an identical component in Chembl, but also ones that have got stereochemical differences in isotopes. Sorry, that protonation should be here. So again, as I say, you know, zinc, you'll have molecules with different protonation. And then obviously you can have any permutations of this. You can have molecules that have got stereochemical and isotope differences, stereochemistry and protonation differences. And you can see a map effectively of all of these different connectivity maps if you actually want to. And the way we've done it in Chembl itself is these again are all hyperlinks, so you can go from these and click on that entry in the particular database. Okay, so just to sort of finish off, really, just to mention that we do have a short UniChEM quick tour on our EBI Train Online course website that you're very welcome to go and have a look at. We will take the recording that we've made of the webinar this afternoon and put that on UniChEM. Oh, sorry, on UniChEM. Put it on YouTube fairly soon. So obviously, John, who was talking at the start, is the person who's done the majority of the work on UniChEM, but you know, there were other people within the Chembl group, sort of past and present, as well as people in some other groups here at EBI who've contributed to this. And John's actually published a couple of papers on UniChEM, one about the just the sort of straight UniChEM matching, and then a subsequent paper on the connectivity searching that, you know, if you want to know more details, then, you know, please go and have a look at those.